Find nearest neighbors instantly with HNSWlib in Python. By the end, you will have a working comparison between exact Euclidean neighbors and an HNSW approximate index. You will measure recall, insert a new point without rebuilding, and run batch queries. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Approximate nearest neighbor search matters because it optimizes query latency while keeping high recall, so searches finish in milliseconds instead of seconds. It trades off memory and exactness, so you accept a small accuracy loss for big speed gains. In practice, HNSW gives near-perfect recall at scale, often handling hundreds of thousands to millions of vectors with very low query time. The intuition is simple. Exact search checks every vector. That is accurate but slow. HNSW builds a graph of vectors and walks the graph to find near neighbors fast. It shines when you need many fast queries on moderate to large collections. One limitation is memory and tuning. You must choose construction and search effort parameters carefully. We will build a tiny pipeline that first computes exact Euclidean neighbors, then builds an HNSW index, compares recall, inserts a new close point, and finally runs a batched query to see multi-query behavior. First, we compute exact distances to form a baseline. This snippet explains a small exact search baseline using a tiny two-dimensional dataset. It stores 6 vectors in an array called X and a single query called Q. The code uses NumPy linl norm, which computes Euclidean distance to get distances from each vector in X to Q. Then NumPy argsort sorts those distances and returns indices in order of closeness. And the code keeps the top 3 results in a variable named top. Finally, it formats and prints 3 ID and distance pairs rounded to 2 decimals, giving a clear exact baseline to compare with AND. This exact baseline is the truth we use to judge HNSW. For tiny data, this is cheap and precise. When your dataset grows, this direct method becomes impractical because you must compute distances to every point. That makes the baseline ideal for correctness checks and for computing recall of the approximate index. Next, we build an HNSW index and query it. This snippet builds an HNSW graph index and retrieves approximate nearest neighbors for the same query. It creates an HNSWlib index configured for L2 space, which means Euclidean distance, and sets the dimension to 2 for these vectors. The call to initialize the index sets maximum capacity, construction effort, graph connectivity M, and a seed for deterministic behavior. The dataset X is added with integer IDs using add items. Then set EF adjusts the search breadth during queries. Finally, KNN query returns the top 3 labels near Q. Raising setf usually increases accuracy, but slows each query. This shows the classic KNN trade-off in one place. The parameter M controls graph connectivity and affects build time and memory. The EF parameter used in construction and set EF affects search thoroughness. If you increase EF, you typically recover more true neighbors, but you spend more time per query. For production, you tune EF against latency and recall targets. Now we measure recall to see how close KNN is to exact. This snippet computes KNN quality by comparing the HNSW results to the exact baseline. The variable exact holds the 3 true nearest IDs from the baseline, while KNN contains the 3 IDs returned by HNSW. The code converts both lists to Python lists of integers and then to sets to compute their intersection. Counting the intersection tells how many true neighbors the index recovered. Dividing that count by the size of exact yields recall at K, a simple accuracy metric where recall is the fraction of true neighbors found among the top K. The output prints recall with 2 decimals, so you can read it easily. Recall at 3 is a quick single query check, but real evaluation averages recall over many queries. If recall is low, increase set F or F construction, or improve vector representations. If recall is already high, you can try lowering F to save time while maintaining acceptable accuracy. Then we insert a new point and observe dynamic updates. This snippet updates the existing HNSW index by adding a new vector that lies very close to the query location. It creates a new vector named newx and assigns it an integer ID called newID. The addItems method inserts this vector into the existing graph without rebuilding from scratch, demonstrating HNSW's ability to accept incremental inserts. After insertion, the code runs KNN query again for the same queue and fetches the top 3 neighbors. Because the new vector is closer than previous points, it appears at the front of the returned list, and the printed IDs show the changed ranking immediately. This behavior highlights a useful production property. You can stream new items into the index, and queries will reflect those inserts right away. Keep in mind, heavy insertion workloads can affect graph structure and search quality. For high insert rates, you may batch inserts or periodically rebuild with a higher construction effort to restore peak accuracy. Finally, we run a batched query to show multi-query performance. This snippet performs a batch nearest neighbor query for 2 queries at once. It stacks the original queue with a second small vector named Q2 to form a query matrix Q. Passing Q into KNN query executes both searches in a single call, returning a label array lab and a distances array DST. The code requests top 1 neighbor for each query, so it reports the single best ID per input. Batch querying reduces per query overhead and mirrors real production use where many queries arrive together and must be served efficiently. The printed 2 IDs show the best match for each query in order. Batching scales better than repeated single queries because it amortizes fixed call overhead and can leverage optimized inner loops. When you serve many queries per second, measure latency and throughput for both single and batched modes to choose what fits your application. Recap: HNSWlib gives extremely fast approximate nearest neighbor search by building a navigable small world graph. Use it when you need low latency at scale and can tolerate slight inexactness. One caveat is that memory and parameter tuning matter. You will tune EF and M to balance speed and recall. Next step: try tuning set EF and the construction EF to meet a specific recall versus latency target, and measure both with a larger query set. If practical IR and fast search help your projects, subscribe and watch the rest of the IR videos.